The Institute of Physics of the Academia Sinica was founded in Shanghai in 1928 and re-established in Nangong, Taipei in 1962. The Institute's primary mission is to promote basic physics research. Its three major research directions are medium and high-energy physics, physics for active and biological systems, physics of quantum materials. The fields of study include particle physics and cosmology, atomic and nuclear physics, condensed matter, materials and surface physics, biophysics, fluid mechanics, and nonlinear physics. The Institute has over 40 research scientists, supported by about 400 research and administrative assistants, graduate students, and doctoral scientists. It's committed to pursuing excellence in research and providing high-quality education and training to future scientists. In the area of medium and high-energy physics, the Taiwan Neutrino Experiment is an international collaborative project conducted at Taiwan's second nuclear power plant. It pursues studies of neutrino magnetic moments, electroweak and coherent interactions, as well as a new detection window to search for low-mass dark matter. The Institute of Physics is also participating in many other international research projects, including the AMS experiment on the International Space Station. This experiment seeks for signals of antimatter and dark matter in space, hopes to unravel the secrets of the Big Bang and possibly new structures. The Institute of Physics, together with other Taiwan institutes, have provided key hardware and software technologies and has established the AMS Payload Operation and Control Center in Taiwan. When the ATLAS experiment at CERN's Large Hadron Collider successfully discovered the Higgs particle, this breakthrough proved that the standard model of particle physics is still valid. The Institute is the first Tier 1 center in Asia and is processing the vast amount of data collected from the ATLAS experiment. In the area of physics for active and biological systems physics research, an interdisciplinary approach combines biological and phenomenological physical models to understand physical mechanisms across the scales of cells, tissues, and organs. Cells are subjected to mechanical influences in their growth microenvironments. To understand the effective dimensionality on cells, we used microfluidic channel technology to blow bubbles of uniform size that produce uniform porous scaffolds. The scaffolds could control the cellular growth in a three-dimensional microenvironment. This technology, already licensed to industry, has tremendous potential in tissue engineering and drug screening applications. Nanometer nanoscale molecular dams are nanometer pinch points formed by nanofabrication, capable of focusing strong electric fields and field gradients. Molecular dams quickly gather trace protein molecules and increase protein concentrations more than 100,000 times within 20 seconds. This will facilitate development of screening chips for cancer and other diseases. The high penetrating power and 3D nanometer resolution of our synchrotron radiation X-ray microscopy unravel the physical mechanism of fireflies' luminescence. Interdisciplinary researchers are combining molecular physics, molecular structures, and pathologic physiology to investigate molecular and cellular behavior from the macroscopic dimensions of organs to micron and nanometer fluid systems. This multi-scale effort seeks to understand how cells maintain efficiency and the basic mechanisms of organ formation, and hopes to ultimately shed light on the emergence and metastasis of cancer cells. Research on the physics of quantum materials mainly includes the growth and characterization of novel quantum materials, fabrication and imaging of nanostructures and interfaces, study of low-temperature physics and superconductivity, spin electronics, and magnetic nanostructure and transport. Recent research results include: as quantum materials represent an important direction in searching for and designing future emergent materials, researchers have been studying the growth and characteristics of quantum materials. Observation and understanding of the distribution of vacancies in iron-based high-temperature superconductors have illuminated the correlation between their degree of orderedness and superconductivity. Working with ferromagnetic topological insulators, researchers for the first time verified that the quantum anomalous Hall effect can be extended to macroscopic and three-dimensional systems. Researchers combined both electron transmission and scanning tunneling microscopy techniques to directly observe nanoscale capillary phenomena and discovered that the ratio of the size of silver nanodroplet to the diameter of carbon nanotube was a critical parameter. Research on a hydrophobic solid water interface discovered that hydrophobic surface can effectively capture gas molecules dissolved in water, and that the gas molecules may form several types of nanometer structures in condensed phases at the interface. To promote forward-looking physics research, the Institute of Physics is constantly acquiring and maintaining advanced equipment and instruments, such as its core facility for nanometer processing, helium liquefaction facility, and precision machine shop. To cultivate future scientists, the Institute hosts the Taiwan International Graduate Program on Nanoscience and Nanotechnology, and also offers numerous interdisciplinary education programs. It promotes international academic interchange and educational outreach activities. The Institute is committed to continuously improve our research and development and explore new territories in physical sciences.